Hi, welcome to another edition of Calculus 3. Today we are going to talk about differentials. For our first lecture, we are going to focus on applications, and then there is going to be a second lecture on theoretical considerations. Let's go ahead and see what this topic looks like. Differentials and increments. You have seen this topic in Calculus 1. So as usual, let's go ahead and review what we had there, and then we see what's the generalization to functions of several variables. So in Calculus 1, you study functions and their derivatives. So I can have a function here such as y is equal to f of x. I want to study how this function increases at a certain point, so I pick some base point, let's call it say x, and then I move a certain distance, so I'll arrive at a new point. Let's call this thing x plus delta x. So this change from x to x plus delta x, we refer to it as the delta x becomes our increment. And suppose the height at origin, at the beginning, is just y. Now the height has changed, it has increased by a certain amount. This one is going to be the increment of y, so this is going to be shown by delta y. Of course, the slope is approximated by delta y over delta x, and when delta x is set to go to 0, that becomes your derivative. So what is delta y? The increment of y, it's f of x at the ending point minus f of x at the starting point. That would be the y increment. We typically want to estimate this change, and the simplest estimation for it is to use the derivative. So we consider the tangent line at the starting point. Tangent line comes up, almost tries to reach that destination that you want, but typically falls short of it. We are going to be at a slightly different place. Let me redraw this picture so that it does not become crowded. So I have a function, it's the same function more or less here. So I had the x, and then I draw the tangent line. I have moved to this location, and the increase that I see here, this one, this increase, this yellow portion, I am comparing it with this blue portion. Well, they are not exactly the same, so we need to refer to it by a different kind of letter, and that is where the differential comes in. This is going to be called dy. This location, exactly the same as before, instead of referring to it with the increment delta x, it's referred to as differential of x added to x. So this, which is exactly the same as that delta x, this is referred to as a differential of x. And this one, this is a differential of y. The main use of this is that dy is very easy to calculate. Dy is f prime of x, which is the slope of this red line, times dx. So in high school you would have referred to this thing as the run. This one would have been your slope, and this one you would have called it the rise. I've changed the terminology on you. We are saying this yellow piece is an approximation for that blue piece. So if I want to calculate delta y, it is approximately same as dy. The approximation gets better if delta x shrinks toward 0. So again, let's remember, this one is referred to as increment of y. This is a differential of y, and the connection between differential and the increment or differential of x is through this formula. Now we want to do the similar idea in higher dimensions. So suppose I have z as a function of x and y. The question is, if I change x and y, what would be the change in z? The formula for the change in z is very easy. Z is going to change to z plus delta z, and that delta z, the increment in z, is going to be the value of the function at incremented x and y. So I change x to x plus delta x, change y to y plus delta y, and from that I subtract the original value, which is f of x and y, and that would be the increment in z. The differential of z, which is an approximation for this and is easier to calculate than calculating this, is the derivative of z with respect to x, partial derivative of z with respect to x, times dx, plus partial of z with respect to y times dy. Let's go ahead and get a sense for what this formula says. What does it try to show? So this is the differential of z, or sometimes referred to as the total differential. Let's take a very simple example we have seen before. Suppose I owner of a farmland. The farmland is in the shape of a rectangle. Its dimensions are x and y, and therefore the area that I own right now, the area is x times y. Now suppose I come into a deal in which I can add to my land by increasing the dimension in this direction by delta x, and the dimension in that y direction by delta y, and still having a rectangle. So my new area the bigger rectangle is going to be now the side x side increased to x plus delta x, and the y side increased to y plus delta y. And if I want to know how much extra I have, that is, what's the difference between the bigger land and the smaller land, I'll show that by delta A, the increment in the area. If I take this thing and multiply it out, so it becomes xy plus x delta y minus y, x plus y delta x plus delta x delta y. if I calculate the new area, which is this, minus the original area, so x, y, and xy cancel each other out, and all I'm left with are these things: x delta y plus y delta x plus delta x delta y. The formula shouldn't overwhelm us. The concept is very simple. How did the area increase? Well, there are three pieces here. Let's color them so that we see it. So I have this piece, I have this one, two rectangles, and a third one. So what's the area of each of these things? These together constitute the increment in the area for me. So this blue one, of course, is delta x times the height y. So this, you can write it as y delta x. The yellow one, you can see this side is x and the thickness is delta y, so that's x delta y. And the green one, the sides are delta x and delta y, so this is delta x delta y. So obviously you see that the y delta x is this y delta x here. X delta y is this term x delta y here. And of course this little piece delta x delta y is this one. Okay, so that is the exact difference between the two areas. Now we kind of reason out that this little green piece is small compared to the blue and yellow one. So on the first quick calculation, we can put this side away and just consider the delta A to be the blue and the yellow one. Now to keep it separate from this, we use the notation differential of A, and now we're going to call this x dy. So this delta y is exactly the same as dy. This delta x also exactly the same as dx. So I have x dy, that's exactly the same as this, and then I have y delta x. Let's write it. And the other one, the blue piece, is of y. Now instead of delta x, we write dx. We just do away with that green portion. So that's where our approximation comes in. So when we are saying these are approximately the same, meaning they don't have to be same, they are close by because one of them has the green piece in it and the other one doesn't. Now let's go ahead look at this thing second way. See what are the we always have this dx and dy in this expression anyway. What's the role of this y and x that is here? This y, if I take the expression for my area xy, differentiate this thing with respect to x, I get this one. So this is really a with respect to x, or partial of a with respect to x. How about x? X is a partial of a with respect to y. So what we have really here, let's write it ay dy, a sub y dy plus a sub x dx. Of course, for a simple example like area of a rectangle, you don't need all this machinery, but this is just to show what happens in general. So what we have, if I have a function that is perhaps a lot more complicated than that area function that we have here, if I want to calculate the change in z and get a quick approximation for that, so differential of z is made out of two pieces. One is a partial of z with respect to x, so you take the partial derivative of this thing with respect to x, multiplied by the increment in x, plus, so there are two sources, and now they have a partial with respect to y, and you add the you multiply with the increment in y, and then you have your answer. Let's go ahead and do some examples so that this is clear. Let's take some function. Suppose I have z is equal to let's say x plus y times cosine of let's say x2y. Some rather complicated expression. So the question is, what's the total differential of z? What is dz? So for that I need to calculate derivative of z with respect to x, and then derivative of z with respect to y, and by then I'm almost 99% done. So derivative of this thing with respect to x, whatever we learned about differentiation we have to apply here. I see a product here, I see a function applied to some interior expression here, so I have to apply the rules of differentiation that I've learned in calculus 1 together with partial differentiation to get this thing done. So derivative of the first times second plus the derivative of second times first, that would be derivative of multiplication. And then in that act I have to do partial derivative with respect to x. Let's go ahead and do it. Derivative of the first expression with respect to x, that's just going to be 1. So it's going to be 1 times cosine of x squared y. Okay, so derivative of this with respect to x is just 1. Next, I have to take a derivative of cosine and multiply with this. So that expression x plus y stays. Derivative of my interior function with respect to x, this is going to be what? Okay, can you calculate it for me? What's the derivative of this interior function with respect to x? It's going to be 2xy, and then derivative of cosine is negative sine of whatever we had before. Okay, now you do the other one for me. How about stopping this video, and then you calculate the zy. So at this point you want to what happened? You want to calculate this thing for yourself and come back and check with me. So derivative with respect to y, again you have to apply the product rule here. Derivative of first times second, second times first, and you have to add them, and all differentiations has to be a partial with respect to y. So derivative of the first again is just 1 times the second, so it's cosine of x squared y. Derivative of second, derivative of cosine I know is going to be negative, so I keep that. I have a factor of x plus y here. Derivative of interior function with respect to y is just x squared, and then derivative of cosine is sine. So what is dz? Is going to be the first expression. Now it became lengthy now. Cosine of x squared y minus x plus y times 2xy times sine of x squared y. All of this, which is partial of z with respect to x, is just times dx. And then the other one expression, whatever it is, so cosine of x squared y minus x plus y times x squared times again sine of x squared y, all of it times differential of y. Okay, at this stage you might be wondering, well, where are we going to actually use anything? This looks too complicated. In fact, just about every engineering experiment is going to ask you to calculate the error propagation for your do the error analysis for your experiment. What is the idea there? Well, whenever you are in a lab, you're calculating things with instruments and such. Every measurement comes with an error. Easy way of describing what the error is going to be a change between what you calculate and what the actual quantity might be. So every measurement comes with a size of an error that is shown typically by like plus or minus 1% or plus or minus 5 part per million or expressions like that. And those kind of expressions simply indicate what could be maximum difference between what you measure and what the actual quantity out there really is. Now, if you are using a formula in which the ingredients are measured with certain degree of error, then the output of that formula also going to have some error. And then we want to figure out what that error is going to be. So we talk about error propagation, meaning if I have a formula in which there is x and y, and I have made mistakes, made errors in measuring x and y, then those errors are going to propagate to anything that is evaluated based on them. So that's called error propagation, and then you do so-called error analysis to figure out what your output, what would be the error of your output quantities. Let's take a simple example. Let's go back and suppose we are back to that rectangle, and so suppose you measure the size of a room or a land or something, and you find out that this site is perhaps say it's a big piece of land, it's 3 miles, and this is going to be say 2 miles. So the area, well, you say 3 times 2 is 6 miles. Well, you know that when you measure a piece of land like that, you can never say you're really sure that this is 3 miles. There is some degree of error in this thing. And suppose our error in each of our measurements is say 0.01 miles, meaning this quantity could have been 3 plus 0.01, or could have been 3 minus 0.01, or anything in between these two values. And suppose on the other side you are making the same error, that the actual quantity could have been 2 plus 0.01 or 2 minus 0.01. So we say let's assume that our measurement is good to plus or minus 0.01 miles. The question is, how about the calculation of the area? What would happen to the area? So the way we go about this thing, we say, so suppose area, well, we know the formula for the area is x times y, and a sub x, the partial of this thing with respect to x is y, partial of this thing with respect to y is x. So if I want to estimate what is the error in my area, I use differential of a, so that is a sub x, then dx plus a sub y dy. So I have two contributions to my overall error. One is because of the error that I make on this side, another one due to the fact that I'm making error on the other side, and the combination of them is going to be my overall error. So let's go ahead do this. Well, a sub x, we calculated it was y dx, and a sub y was x dy, exactly what we had said before. So differential of a, which means the error that is propagated from the error of measurement of the sides to the whole area, is going to be y, which is 2, times dx. Dx we have assumed it to be 0.01. It's plus or minus point. Let's write it plus or minus 0.01, and then x is 3 times plus or minus 0.01 again. So it becomes 5 times 0.01 plus or minus. So that became plus or minus 0.05. So we can say the area, which would have normally calculated as 2 times 3 or 3 times 2 as 6, but now we can say the true measurement is somewhere between 6 plus 0.05 and 6 minus 0.05. So the area is the magnitude of the error in calculation of the area is going to be plus or minus 0.05. Now when you go to your engineering labs and do these things, of course you're going to be dealing with formulas a lot more complicated than this. You have to calculate your partials and then multiply and figure out what the overall error going to be. One thing you have to pay attention to in those cases is that we never allow the errors to cancel each other out. So regardless of the magnitude of error that we have in each direction, if one of these derivatives turned out to be negative and the other one was positive, we have to take their absolute value and multiply by the differentials and add them up. Essentially err on the conservative side, that one error is not going to be allowed to cancel another error. Okay, let's go ahead and do some examples where pure calculation is given to us and then we are asked to estimate something by using the concept of differentials. So a typical example here, for example, I pick this one, say it's a 2 point, this is problem, one of the problems in your textbook, 2.01 squared times 9.02 minus 2 squared times 9. So the issue is use differentials to estimate the following quantity. The problem might sound a bit silly that, okay, I type this thing on a calculator and the calculator is going to spit out some number. Well, that's your number. Why do you want me to estimate anything? I already have this quantity. So this is a practice for how to use differentials, to use it in your experimental settings and calculate certain things quickly. So we look at this thing and say, oh, what was the original expression? Some quantity being squared times some other quantity, and then these two values are changed slightly. So we are going to assign some variable names to these things. This 2 that's being changed to 2.01, let's call it x. Then this 9 that's changing to 9.02, let's call it y. And we have a x squared times y. So I define a function, first of all, z is equal to x squared times y. Okay, so from the subtraction you're supposed to do, you focus on one of these things and convert it to a formula in several variables. Then what you want to calculate here is a differential of the increment in z. We said this is supposed to be x plus delta x squared times y plus delta y. This is the new value of this thing minus the original value of it. So you see that this what I have written here looks pretty same as that, with the delta x being 0.01 and our delta y being 0.02. So again, you can of course just type this thing on a calculator and figure it out, but that is not the intention of the text or homework problem and such. Instead, what we are expected to do is the following: to estimate it, meaning to To estimate it, we are using the total differential of z. Total differential of z is going to be z with respect to x dx, z with respect to y dy. So z with respect to x, derivative of this thing with respect to x is 2xy, and this is dx, and the derivative with respect to y is just x squared dy. So that's our dz. Now we put our quantities in it. So let's put it next to this. X was 2 and y was 9. So here we put our numbers. X is replaced by 2, y is replaced by 9. This is same as the increment and differentials are the same for our independent variables. So dx is going to be 0.01. X squared is 2 squared, and differential of y is 0.02. Now at this stage you can go ahead and use your calculator to figure this one out and report that as your estimate of this quantity. This is fine, but using that in the calculator and getting an answer out, you're typically going to be off by at the last couple of digits and such. So you want to come here and perhaps simplify this thing by hand a little bit. This is 36 times 0.01, and then it's 4 times 0.02. So this is going to be 0.36, and this is going to be 0.08, and then total is going to be 0.44, I believe. So what we calculated is that dz is 0.44, and that's an approximation for what this quantity is going to be, delta. That's going to be approximation for delta z. So to be sure that you have done this correctly, you can try to actually calculate it on a calculator, meaning go ahead and calculate this on a calculator. So let me see, I can do this thing on my calculator here. Times 9.02, and then minus 2 squared times 9, so minus 36. So when I do this on calculator, I get 0.441702. That's the exact value of this quantity. What we are getting is just 0.44, so we are recovering this much of the answer, and the rest of it is essentially gets thrown to the side. That extra piece that is not calculated anymore is this extra little piece here that we are kind of sacrificing for the speed of calculation. Okay, so this is the topic of differentials as you use it in both mathematics and physics and engineering. But there's also another side to this that is kind of pure math and as a foundation for courses called real analysis or advanced calculus. I put that in a separate lecture, essentially as an optional additional reading. Okay, until the next lecture, good luck and God bless.